All right. So thanks to the organizers for putting this event together. I'm going to keep looking over here, even though my screen is over here. Okay, so I'm Eric. I'm presenting our new work on adapting response time analyses from studies on human visual attention and perception for use in explaining visual processes in artificial visual perception. I also want to take a moment to acknowledge my co-author Shashank's equal contribution to the paper. It's giving me a problem. There we go. So our research is motivated by the question, how would you explain AI decisions if you couldn't look inside the black box? This seems like a ridiculous thing to do. After all, why would you ignore pertinent information? But most techniques developed for XAI depend on privileged access to the architecture and parameters of the model in question. For example, querying the gradient in order to produce saliency maps, or performing activation maximization to produce feature visualizations. But we can easily imagine situations where an explanation is desirable, but inspection of the model or its parameters is impossible. Should we trust the creators of proprietary algorithms to tell us how they work? In the interest of fairness, safety, and oversight, we will need ways to produce explanations for models that we are not allowed to inspect. In this example, we have AlexNet taking an image as input and responding with its top 5 best guesses at what the image contains. Most XAI techniques depend strongly on knowing the details of the model and being able to interact with it and to inspect its nuts and bolts. We are proposing that it is important to be able to produce explanations without knowing anything about the model itself. How would you explain AlexNet's decision if you only had access to the input and the output? In other words, if you were really treating it as a black box. Well, fortunately for XAI practitioners wanting to generate explanations from outside the black box, there is a strong precedent. Cognitive psychologists have had a very similar black box problem for over 150 years. Before modern neuroimaging techniques, psychologists were unable to look inside their black box, which is the brain, of course. And they produced compelling theories of human mind that were generated exclusively from curated input and observed behavior. Historically, the first example of this was Donder's use of response time measurements to identify the stages of processing involved in perceiving and responding to auditory stimuli. So I've reproduced some of his data from 1868 here on the left. Donder's asked participants to repeat a syllable that was known to them in advance, or to repeat a syllable they were unprepared for. So this is the repeat condition and the classify plus repeat condition. The additional time, so the difference in time there, required to make the second type of response was interpreted as evidence for an additional stage of information processing in the human mind. And this stage was dedicated to classifying incoming stimuli and selecting the appropriate response out of several alternatives. So it's a nice example of how, from outside of the black box, the psychologist was able to sort of identify the stages of processing and make an explanation for how we do this. We want to use a similar logic applied to artificial neural networks, where we examine response time from outside the black box to make inferences about sequential stages of processing, given tasks or stimuli of varying difficulty. Now, using response time methods for most artificial neural networks doesn't make any sense because they generally perform a fixed number of operations on each forward pass, regardless of the input. In order to conduct response time analyses, we need a distribution of response times and a meaningful relationship between the time of processing and the task. A new class of models provides those two conditions that we require for RT methods. Dynamic inference models can use conditional computation to permit early exits based on the confidence of intermediate classifiers if some confidence threshold or computational budget has been reached. These models are useful in devices with limited computational capacity or time-constrained decision-making, and they're gaining popularity. So over here, referring back to our AlexNet toy example, we can imagine appending auxiliary classifiers to intermediate layers of the network and forcing the forward pass to quit early if the computational budget or the confidence threshold is met. This would have the side effect of making the decision with features only from earlier layers. So that may result in some incorrect classification. And we can just imagine that this decision, for example, is made using only very primitive features. Whereas if we put the confidence threshold at very high, we would need the model to go all the way through and use all the features. We conducted our experiments on MSDNet, multi-scale dense-net, which uses conditional computation and 5 auxiliary classifiers with an early exit architecture. If hierarchical feature space is correlated with model depth, and conditional computation allows early exits, then we can make predictions about the relationship between feature space and response time. Specifically, decisions that depend on higher order feature space should take longer, And critically, we don't need to be able to inspect the model or its parameters to do this. We just need to know the input and record the output. It's not a perfect correlation between features and or feature space, the depth of the model, and time, because this architecture does permit sharing between layers, sharing features between layers, but there is a relationship between the position of the intermediate classifier and its performance. So for our first experiment, we compared response time for images from ImageNet and ObjectNet, which is a test set designed to contain non-canonical object features that are generally absent from most training data for object recognition. So here's an image from the ObjectNet paper. Here is a standard ImageNet chair. It is a very canonical chair. And here are 5 versions of ObjectNet chairs. So you can see the ObjectNet chairs contain many images from odd angles or weird viewpoints on unusual backgrounds, things that you don't normally see in ImageNet. State-of-the-art models that are trained for object recognition exhibit major drops in performance, up to 45% when they're tested on ObjectNet. So we know that there's a different set of features, and it's a more complex set of features required to successfully classify ObjectNet images versus ImageNet. So here's the prediction for the first experiment. If classifying objects in ObjectNet versus ImageNet depends on features that are composed in different layers, a dynamic inference model such as MSDNet should produce a response time profile that bears some connection to the way it processes feature space. In other words, objects composed of more complex features should take longer to reach a decision. So here are the results. A bit more on the methodology. We measured response time as the system clock time elapsed for the forward pass, from the time it starts until the time it quits, and that is variable depending on where it exits. And we did that across the entire range of confidence thresholds. In other words, we measured how long the model took to reach a decision given all possible values of minimum confidence. If one classifier was insufficiently confident, the forward pass would proceed to the next classifier until any classifier produced a response with adequate confidence. So here on the left, I've highlighted an ImageNet chair in blue and an ObjectNet chair in red, and I'll use those colors going forward to refer to those 2 image sets. The second panel contains results from 5 randomly selected chairs from ImageNet and 5 from ObjectNet. This is just an illustrative case. The vertical axis shows the mean early exit response time, so that's just time elapsed. The horizontal axis is the confidence threshold, and the second vertical axis shows the response time corresponding to all 5 intermediate classifiers, so those are constant. Okay, so this pattern forms a step function because the response time for any given classifier is always constant. If that classifier is insufficiently confident, it jumps up to the next classifier. So that's why we get these staircases. The ideal performance in this case is a backwards L, where the first classifier will be adequately confident for all threshold values. So what we can see from this quick snapshot of 5 chairs from each set is that MSDNet is much better, is performing much better, much faster, is reaching the same confidence level much faster for the ImageNet chairs versus the ObjectNet chairs. The third panel here shows the mean response time for the 2 test sets across all images. So that's 50,000 ImageNet images and 5,000 ObjectNet images. The inset here shows the grand mean. So we can clearly see that response time analyses reveal large differences in processing difficulty between the 2 test sets. Oh wait, I forgot to say something. So this pattern results as proof of concept for using response time analyses to document task difficulty. But we can't make very strong claims about feature processing because there are so many differences in the input between ImageNet and ObjectNet. To do that, we need input with more carefully controlled features. So let's take a look at the scene grammar dataset designed for experiments with human subjects, or CGRAM for short. Humans use object-object and object-scene relationships to guide visual attention in naturalistic environments and to make sense of scenes. It turns out we're very sensitive to these high-level relationships. Scene grammar effects can be tested with the carefully created CGRAM database, which contains 62 sets of 4 images with different combinations of semantic and syntactic scene grammar violations. And I'll show you in a moment what those look like. The creators of CGRAM were very careful to control for pixel level differences across the 4 image manipulations so that observed differences in human behavior could be attributed to the semantic and syntactic violations. So here's a scene with consistent scene grammar, and as you can see, it's just the kitchen and there's nothing out of place. A semantic inconsistency occurs when a consistent object is replaced with one that doesn't normally appear in scenes like this, such as this clock in the drying rack. Any classification that depends on that feature is using a high-level representation for the relationship between objects, other objects, and scenes. A syntactic inconsistency occurs when an object that is normally occurring in this scene is found in an unusual place, like this floating pot lid. CGRAM also contains scenes with semantic and syntactic inconsistencies, so we can see whether there are dissociable or interactive effects of both violation types. This is some human data just to show that this effect occurs in humans, and dwell time is a measure of how long we spend foveating on a certain part of a scene. What we can see is that people attend to semantic and syntactic inconsistencies in CGRAM much longer than the consistent scenes. So the analysis is the same as the earlier experiment with ObjectNet and ImageNet. The left panel here again shows step plots for our illustrative case. This is scene 53, it's just one of the 62 scenes. What we can see is that the image with consistent scene grammar is performing much better than the images with inconsistent scene grammar. And then on the right panel, we have our mean taken across all 62 scenes. And the inset here is the grand mean. So as we can see, the fastest response time is for consistent images and slower response times for images with inconsistent semantics specifically. That's these two categories. We confirm these patterns with the repeated measures Anova. The Anova revealed a main effect for semantic inconsistencies, not syntactic inconsistencies. This means that the model was selectively sensitive to features that defined object-object relationships. Interestingly, the response time profile for consistent images appears to deviate from the rest in the first and second classifiers, which means that the features MSDNet struggled with in the images with inconsistent semantics were not confidently processed prior to the earlier classifiers. Using these response time plots, we can start to make inferences about where in the model different features are processed, and that's these deviations here. Lastly, we can also predict when this effect should not occur. So there's a clone set of images with the critical object removed, and we predict that those RT plots should collapse upon each other, and they do. So I know I'm just about 30 seconds over time, so I'm gonna skip the conclusions and just say we can use these kind of outside the box analyses to form expectations for when and how models should perform in situations where explanations are desirable, but privileged access to the model is denied. Thanks very much.